All right, free response question number 2. We have a collision question. So I'm just going to do this with numbers the way y'all did. 0.3, moving to the right. Make that a positive 2.0. Collides with the cart, 0.10, moving to the left. Make that a negative 3.0. Equals 0.10, moving to the right at 1.2, plus 0.3, moving at some speed that we do not know. So I'm going to simplify a couple things here. We're going to get 0.6 minus 0.3 equals 0.12 plus 0.3 times v. We're going to end up getting 0.18 equals 0.3 v. So v is going to, 0.18 times 0.3 v. So we're going to end up getting 0.6 meters per second to the right. You got to put that direction. Now, is this collision elastic? Okay. I'm just going to tell you right now. No. The reason is kinetic energy is not conserved. And you need to show me that. So 1/2 times 0.3 times 2 squared plus 1/2 times 0.1 times negative 3 squared. Okay, so that's the initial. And then compare that to 1/2 times 0.3 times 0.6 squared plus 1/2 times 0.1 times 1.2 squared. We are clearly losing energy. All right. Now we got this cart hitting a spring and compressing it. So what happens is all this kinetic energy gets stored as spring energy. So we got here. Well, we don't know this side, but we do know that all this energy gets converted. So we got 1/2 times 0.3 times it's 0.12 squared, and that's going to give us 0.072 joules of energy. Awesome. Now we want to know the compression of the spring, so we're just going to continue. 0.072 equals 1/2 times k times 0.1 squared, and we're going to actually end up getting a k of 14.4. Now, here, if we have a nonlinear spring, get the potential energy function, bx cubed, okay? dx, the negative of that integral should give you u. So that's bx to the 4th over 4. And then we have all that 1/2 mv squared from before becoming bx to the 4th over 4. So we have 0.072 equals b times 0.1 to the 4th divided by 4. When we isolate b, we should be getting something around like 2,880. Whatever the units on this are, joules over meters to the 4th. Yeah. Awesome. Now, this third question here, you got to be careful, okay? So, you actually need to draw a best fit line. Like that. And I'll tell you, what I ended up using for my lines, I ended up using the following. I used this point and this point, so this ended up being like 0.45, comma 1.50, and I ended up using 0.37, I eyeballed it, and then 1.00. So the slope, A, is going to be delta V over delta T. That's going to be like 1.25 minus 1.0 over 0.45 minus 0.37. And when I worked that out, that was about 3.1 meters per second squared. You should be getting something between like 2.7 and 3.3 for your answer. Okay. Now, we want to get the rotational inertia of the disk. So continuing with that idea, first, I know that mg minus tension makes the mass accelerate. I also know that the torque is what makes it spin, and that torque comes from the rope. So we get the tension times the lever arm, I times, I'm going to write it as A over R. And so I'll have these two equations to kind of stick together. So I'll get I as mg minus ma r squared over A. And when I put in my numbers, I got 0.0011. Okay. So you'll need to do the algebra for this because I'm getting tired. Okay. Then we want the angular momentum. That's L is I times omega. That's going to be, so to get omega, that's going to be alpha times T, which is going to be A over R times T. So L is going to be I times 3.1 times 0.45 divided by the radius, which is 0.1. I got an L of 0.015. Now we're going to replace the wheel with a disk. What's going to happen to the acceleration? It's going to be less than, and here's why. You get a bigger I. So harder to spin, and therefore harder to accelerate. So that is the answer to the last 2 free response questions on the AP exam. So I will put these on Haiku, and you'll have complete solutions to the exam.